Hi everyone, welcome to our physics class. This is current electricity part 7. In the previous class, we learned about two very important 5-mark derivations. That is derivation of expression for equivalent resistance of two resistors connected in series and equivalent resistance of two resistors connected in parallel and branch current formula. In this class, we are going to discuss about very important terms, that is the meaning of cell, EMF of a cell, terminal potential difference of a cell, internal resistance of a cell, and Ohm's law that is applied to a very simple closed circuit, and derivation of the relation connecting between electric current, EMF, internal resistance and external resistance. And next, very important 5-mark derivation, it is derivation of expression for equivalent EMF of two cells connected in series. Okay, well, so let's start today's class. Okay, so first let us discuss about the meaning of a cell. Actually, a cell is a device which provides the necessary potential difference to an electric circuit to maintain a continuous flow of current in it. What is the meaning of cell? Cell is device. Cell is a device which provides the necessary potential difference. Why? For which purpose? To maintain a continuous flow of current. Where? In the circuit. That is the meaning of a cell. Cell is a device which provides the necessary potential difference to an electric circuit to maintain a continuous flow of current in the circuit. So what is the meaning of electric cell? Actually, this is a very simple chemical cell. So this is a device which converts the chemical energy into electric energy. So electric cell means device which converts the chemical energy into the electrical energy. Actually here these are two electrodes. One is negatively charged and another one is positively charged. This is made from magnesium and this rod is made from copper. So both electrodes are dipped in electrolyte. So this is copper sulfate solution. So what happens? So one rod actually gets negatively charged and another one gets positively charged. So here there is a potential difference between the two terminals. Okay. So actually the potential difference across the terminals. So these are the terminals. This is positive terminal. This one is negative terminal. The potential difference across the terminals, the potential difference across the terminals of the cell when the cell is in open circuit. No current is being drawn from the cell. That is called EMF of the cell. EMF means electromotive force. Electromotive force. That means this is not a force. Okay, this is not a force. This is the potential difference across the terminals of the cell when the cell is in open circuit, or the potential difference across terminals of the cell when no current is being drawn from the cell. Potential difference across terminals of the cell is in open circuit, or when no current is being drawn from the cell. Actually, that is the meaning of EMF. EMF, EMF means electromotive force. Okay, what is the meaning of cell? A cell is a device which provides the necessary potential difference to an electric circuit to maintain the continuous flow of current in the circuit. What is the meaning of electric cell? It is a device which converts the chemical energy into electric energy, electrical energy. So here let us consider a bulb that is connected across this cell, electric cell. So what happens? Bulb will glow because here the electrons are moving from magnesium rod to negative electrode to positive electrode. So we can replace this bulb to a multimeter or voltmeter. Okay. So the potential difference across the terminals of the cell when the cell is in open circuit. So in that case, the reading of voltmeter, that is EMF of a cell. Okay. In that way, we have to find out the EMF. How do you find out the EMF of a cell? That is actually very important. So in the open circuit, let us consider voltmeter. Okay, voltmeter is connected. Actually, voltmeter having two terminals. One is positive terminal, another one is negative terminal. That is connected across this cell. Then we will get the potential difference. Potential difference across the cell, and the cell is in open circuit. Actually, that voltmeter reading is EMF. EMF of a cell. What is the meaning of EMF of a cell? The potential difference across the terminals of the cell, potential difference across terminals of the cell when the cell is in open circuit. No current is being drawn from the cell. Or the amount of work done. So EMF of a cell that can also be defined as amount of work done in moving, in transferring a unit positive test charge once around the circuit. Okay, once around the circuit. So that is also called EMF. EMF of a cell that can also be defined as what? Amount of work done in transferring. Amount of work done in transferring a unit positive test charge once around the circuit. That is called EMF of a cell. Okay, so EMF that is measured in terms of volt. So what is the mathematical expression for EMF? Is very important. EMF, that is actually the ratio of work done divided by charge. Work done to the charge. EMF of a cell is measured in terms of volt. So 1 volt is equal to 1 joule divided by 1 coulomb. Okay, when EMF of a cell is said to be 1 volt. If 1 joule is energy, 1 joule is energy required for the flow of 1 coulomb of charge in the complete closed circuit, then the EMF of cell will be 1 volt. 1 joule of definition is very simple. 1 joule of energy is required. 1 joule of energy that is required for the flow of 1 coulomb. 1 joule of energy is required for the flow of 1 coulomb of charge in the complete closed circuit. Then the EMF of the cell is said to be 1 volt. Okay, so one EMF of a cell is said to be 2 volt. So 2 joule of work, 2 joule of energy that is required for the flow of 1 coulomb of charge in the complete closed circuit. And the EMF of cell is 2 volt. 3 joule is the energy. 3 joule is the energy that is required for the flow of 1 coulomb of charge in the complete closed circuit. Then what is the EMF? 3 volt. Usually, the cells that is of two types. One is primary cell, and another one is secondary cell. The primary cell means a cell which cannot be recharged. For example, dry cell, Lackland cell, Daniel cell. Those are the primary cells. Those cells cannot be recharged. A cell which cannot be recharged, cell which cannot be recharged, that is primary cell. A cell which can be recharged, that is secondary cell. So example for primary cell is Daniel cell. Actually, Daniel cell having EMF that is 1.08 volt. Daniel cell having EMF 1.08 volt. This is primary cell. Okay, Lackland cell. Lackland cell, and this one having EMF that is 1.45 volt. So both are primary cells. Secondary cell means cell which can be recharged. For example, lead acid accumulator. Lead acid accumulator. That is actually the secondary cell that can be recharged. Okay. Cell which cannot be recharged is primary cell. Cell which can be recharged, that is secondary cell. Okay. So those are actually the types of cell. What is the meaning of cell? A cell is a device which provides a necessary potential difference to an electric circuit to maintain continuous flow of current in it. Okay. So what is the meaning of EMF of a cell? The potential difference across the terminals of the cell when the cell is in open circuit. The potential difference across terminals of the cell when no current is being drawn from the cell. So our amount of work done in transferring a unit positive test charge once around the circuit. Amount of work done in transferring a unit positive test charge once around the circuit, that is also called the EMF. When EMF of a cell is said to be 1 volt, 1 joule is energy, 1 joule of energy, 1 joule is energy that is required for the flow of 1 joule of energy that is required for the flow of 1 coulomb of charge 1 coulomb of charge in the complete closed circuit. Complete closed circuit. Then the EMF of the cell will be 1 volt. 1 joule of energy is required for the flow of 1 coulomb of charge in complete closed circuit. Then the EMF of the cell is said to be 1 volt. So what is the SI unit of EMF? That is 1 volt or joule per coulomb. Okay, the SI unit of EMF of the cell is volt or joule per coulomb. So EMF is not a force, it is the potential difference between terminals. Potential difference between terminals of cell when the cell is in open circuit. Okay. So the next a very important term, that is terminal potential difference. So terminal potential difference means the potential difference across the terminals of the cell. Potential difference across terminals of the cell when the cell is in closed circuit. What is the meaning of terminal potential difference? It is very simple definition. The potential difference across the terminals of the cell when the cell that is in a closed circuit. The current is being drawn. No current is being drawn, that is EMF. Current is being drawn from the cell, that is terminal potential difference, and this is also measured in terms of volt. But usually terminal potential difference, that is less as compared to EMF of a cell. Terminal potential difference is always less than the EMF of a cell. EMF of a cell, that is more than the terminal potential difference. Okay, what is the meaning of terminal potential difference? The potential difference across the terminals of the cell. Potential difference across terminals of the cell when the cell is in a closed circuit, or the potential difference across terminals of the cell when current is being drawn from the cell. So that is the meaning of terminal potential difference. And the next, a very important term, that is internal resistance of a cell. So the internal resistance of a cell means, it is very simple. The solution of a cell that will causes hindrance. Hindrance means solution of a cell causes certain hindrance. Certain hindrance to the flow of current. Solution of a cell causes certain hindrance. Hindrance to the flow of current. Hindrance means certain opposition. So actually that is the meaning of internal resistance of a cell. Opposition offered by cell. Actually cell itself offers a certain opposition. Okay, the opposition offered by a cell to the flow of current. Okay, so that is the meaning of internal resistance of a cell. The symbolic representation of internal resistance is small r. Small r is the symbolic representation of internal resistance of a cell. Actually, internal resistance is directly proportional to separation between the electrons. Okay, so L is the separation between the electrons, and internal resistance is inversely proportional to area of immersed portion of the electrode. So it depends on two factors. Number one, separation. The separation increases. What happens? The resistance will increase. Suppose if the separation between the electrodes decreases, so the resistance will decrease. Okay. The separation between the electrodes decreases. What happens to the internal resistance? Decreases. Suppose if the separation increases, then internal resistance increases. Okay, and it depends. Internal resistance depends on the area of immersed portion of the electrode. So suppose if the area of immersed portion, that is, decreases, what happens? The internal resistance, area of immersed portion decreases. So then what happens to the internal resistance? Internal resistance will increase. Suppose both electrodes are taken out from solution, electrolyte. So then what is the value of A? What is the value of A? Both the electrodes are taken out from electrolyte. The area of immersed portion is completely equal to 0. Then cell offers how much resistance? That is infinite resistance. That means no current is drawn from the cell. Okay, so this point is very important. If A is equal to 0 or becomes infinity. So what is the meaning of internal resistance of a cell? Internal resistance of a cell means the solution of a cell causes causes certain hindrance certain hindrance to the flow of current. That is the meaning of internal resistance of a cell, or simply the opposition offered by cell to the flow of current. So that is called the internal resistance of a cell. Okay, so these four terms are very, very important. Number one, cell. Cell is the device which provides the necessary potential difference. Cell is the device which provides what? Necessary potential difference to an electric circuit to maintain the continuous flow of current in it. Okay, so what is the meaning of primary cell? Cell which cannot be recharged. Cell which can be recharged, that is secondary cell. What is the meaning of EMF of a cell? The potential difference across the terminals of the cell when no current is being drawn from the cell, when the cell is in open circuit, or amount of work done in transferring a unit positive test charge once around the circuit. Amount of work done in transferring a unit positive test charge once around the circuit, that is called EMF of a cell. That is measured in terms of volt. EMF means electromotive force. It is not a force. This is the potential difference across the terminals of the cell when the cell is in open circuit, when no current is being drawn from the cell. When the EMF of a cell is said to be 1 volt, 1 joule of energy that is required for the flow of 1 coulomb of charge in complete closed circuit. Then the EMF of cell is said to be 1 volt. So what is the meaning of terminal potential difference of a cell? The potential difference across terminals of the cell, potential difference across terminals of the cell when the cell is in closed circuit, or the potential difference across terminals of the cell when current is being drawn from the cell. So, and the next very important term, internal resistance of a cell. So internal resistance of a cell means the solution of a cell causes certain hindrance to the flow of current or opposition offered by a cell to the flow of current. So it depends on separation between the electrodes. So how does internal resistance of a cell depends on separation between the electrodes, that is directly proportional. So and area of immersed portion of the electrodes. So how does internal resistance of a cell depends on area of immersed portion of electrodes, that is inversely proportional, and that is also depends on concentration, nature, temperature and concentration of electrolyte. So now combining these two equations, actually we will get R is proportional to L divided by A. So R is equal to, remove the proportionality, we will get the proportion of the constant C L divided by A. So this is the mathematical expression for internal resistance of a cell. It depends on temperature, nature, temperature and concentration. Nature, temperature and concentration of electrode light, separation between the electrodes and area of immersed portion of electrodes. Area of immersed portion of electrodes. Okay, the next topic, and this is a very important 3-mark derivation. Obtain the expression for current. Obtain the expression for current drawn by external resistance using Ohm's law. Expression for current drawn by external resistance by using Ohm's law. Okay. First here, let us consider a cell. Let's consider a cell. What is the meaning of cell? Cell is a device which provides the necessary potential difference to an electric circuit to maintain continuous flow of current in the circuit. Okay. So it is having EMF. It is E. What is the meaning of EMF? Potential difference across terminals of the cell when the cell is in open circuit. No current is being drawn from the cell. E is the EMF of the cell. So, and internal resistance R. Internal resistance is R. Internal resistance means opposition offered by cell to the flow of current. So internal resistance connected to an external resistance, capital R. Consider R. So here internal resistance and external resistance both are connected in series. Okay. So actually current is always drawn from the positive terminal of the cell. I is the current drawn from the cell. It is flowing through the resistor. Okay. So here is also the current is the same current is flowing through the internal resistance. Current flowing through external resistance, internal resistance, both are same because the external resistance that is connected in series with the internal resistance. Okay. So actually here we have to derive the connecting between relation connecting between electric current, EMF, internal resistance and external resistance by using Ohm's law. Actually, this is Ohm's law that is applied to a very simple closed circuit. This is Ohm's law applied to a simple closed circuit. Okay. Well, let's start derivation. Derivation is very simple. First, by the definition of EMF, by the definition, by the definition of EMF. Definition. What is the definition? The amount of work done in transferring a unit positive test charge once around the circuit. Consider this point as A, this point as B. Actually, here work done is divided into two parts. Number one, work done in transferring a unit positive test charge from A to B against external resistance. Okay, it is one part of work done. What is that? Work done in carrying, a unit charge. Work done in carrying a unit charge from A to B against capital R. This is one part of work done, and another part is work done in carrying unit charge from B to A against small r. Okay, and this is totally EMF. EMF means amount of work done in transferring a unit charge, amount of work done in transferring or carrying unit charge once around the circuit, right? So EMF that is equal to work done in carrying unit charge from A to B against capital R, external resistance, is the potential difference across the capital R. So work done in carrying unit charge from B to A against small r, that is potential difference across the internal resistance. So the EMF is equal to V is I into, or according to Ohm's law, V is equal to IR. Potential difference across capital R is IR. current flowing through capital R is I, potential difference is I into R, right? So V dash, this is the value of V dash, is I into small r. This is potential difference across small r, I into small r. So E is equal to I is take it as common or plus or. So finally we will get I is equal to E divided by R plus R. I is equal to E divided by R plus R. Is this? This is the relation connecting between electric current EMF of a cell, external resistance and internal resistance. I is equal to E divided by R plus R plus R. So this is a very important derivation. This is a very important derivation for 3 mark. Okay. And here, what is the terminal potential difference across AB? So it is very important for CET. So what is the terminal potential difference? Terminal potential difference across AB. Terminal potential difference across AB is V is equal to IR. This is according to Ohm's law. This is not EMF. What is this? Terminal potential difference. Actually, terminal potential difference that is always less. This point is also very, very important. Terminal potential difference is always less than the EMF of a cell. Okay. So V is equal to, what is the value of I? I value is E divided by R plus R into R. So E divided by, so here R is taken as common, 1 plus small r divided by capital R into R get cancelled. And finally we will get terminal potential difference in terms of EMF, internal resistance and external resistance. That is V is equal to E divided by 1 plus V is equal to E divided by 1 plus small r divided by capital R. Okay. So actually V can also be written in the form of, look at this equation, V that can also be written in the form of V is equal to E minus V dash, right? What is the meaning of V dash? V dash is I R. So this is also the very important mathematical expression. V is equal to E minus IR. So this is the terminal potential difference. This is terminal potential difference across the cell in terms of EMF, electric current and internal resistance. Actually this equation is very, very important. Okay. So this is the expression for terminal potential difference across the cell, terminal potential difference of a cell in terms of EMF, internal resistance and external resistance. This is terminal potential difference of a cell. This is the expression for terminal potential difference of a cell in terms of EMF, electric current, and internal resistance. Okay, and the next very important point. So actually, from this equation, so this equation can also be written in the form of all this as equation number 1. This is from equation 1. And equation 1, I into smaller, I into smaller, that is equal to I into smaller, that is equal to E minus I into R, that is V, right? So I into small r. Here V is taken as common. V of E divided by V minus 1. Okay. So small r is equal to V divided by I, V divided by I of E divided by V minus 1. So V divided by I, V divided by I is capital R, right? So small r is equal to capital R of E divided by V, E divided by V minus 1. So this is also a very important mathematical expression. Small r is equal to capital R of E divided by V minus 1. So this is a mathematical expression for internal resistance in terms of external resistance, EMF of the cell, terminal potential difference. Okay, so next point, and this is very important for 2 mark. Okay, so when the terminal potential difference of a cell is equal to its EMF, or show that terminal potential difference of a cell is equal to EMF. So when the terminal potential difference of a cell is equal to EMF. Okay, so here first let us consider this mathematical expression. According to Ohm's law, V is equal to I or, is it right? So V is equal, what is the value of I? That is E divided by R plus R. Okay. E divided by R plus R. So E R of here capital R, that is taken as outside, and we will get 1 plus small r divided by capital R. So capital R get cancels, and finally we will get V is equal to E divided by 1 plus small r divided by capital R. So this is a very important equation. So from this equation, we can prove V is equal to E by taking this equation. Okay. So when V is equal to E, there are two possibilities. One is if R is equal to 0. If R is equal to 0, then what happens? 1 plus 0 divided by anything is 0, right? So then V is equal to E. but practically internal resistance of a cell should not be equal to 0. If R is equal to 0, then V is equal to E. But practically internal resistance of a cell is not equal to 0. So another possibility, that is capital R becomes infinity. So when capital R, that means external resistance, becomes infinity, if the cell is an open circuit, this point is also very, very important. If if the if cell is in open circuit, the cell is in open circuit, then the external resistance becomes infinity. So anything infinity means 1 by 0. Anything divided by infinity is 0, right? So then V is equal to, find therefore V is equal to E, right? So when terminal potential difference is equal to EMF, that is very simple. The cell is in open circuit, then external resistance of a cell becomes infinity, then terminal potential difference, that is exactly equal to EMF, exactly equal to EMF of a cell. Okay, so the next topic, derive the expression for equivalent EMF and equivalent internal resistance when two different cells are connected in series. And this is a very, very important 5-mark derivation. Okay, first here, let us consider two cells. Okay, this is the first one. Now consider the EMF of the first cell, that is E1, and this cell having the internal resistance is R1. Okay, so let us consider this point as A, this point as B, this point as C. So from A and B, which point having more potential? Actually, point A having more potential as compared to point B, because it is very close to the positive terminal. Okay, the potential difference across the first cell is VA minus VB. Let us consider VAB. VAB, that is the terminal potential difference across the first cell. The terminal potential difference across the first cell, that is exactly equal to VA minus VB. This point is also very, very important. Okay, and this is the second cell. Let's consider the EMF of the second cell is E2 and internal resistance is R2. Okay, so what is the terminal potential difference across second cell? So that is VBC. VBC is, so VB minus VC. This is terminal potential difference across the second cell. Okay, so when the two cells are said to be connected in series, the positive terminal of one cell is connected to negative terminal of another cell. or the negative terminal of one cell that is connected to the positive terminal of another cell, then the cells are said to be connected in series. Okay, if the cells are connected in series, the 2 points very important. Number one, the current drawn, the current drawn from the each cell it is same. The current drawn from each cell that is same. That but the terminal potential difference, terminal potential difference across each cell that is not same, that is different, and the net terminal potential difference across the combination. What is that? That is VAC. VAC is actually VA minus VC. So actually VAC that is equal to VAB plus VBC. So VAB is VA minus VB plus VBC is VB minus VC. So VB cancels. So finally we will get VA minus VC. Is it not? VAB is how much? VAB is VA minus VB. So VBC is VB minus VC. So VB cancels. VAC is VA minus VC. So the net terminal potential difference across the series combination that is exactly equal to the sum of terminal potential differences across the individual cells. Okay. So when this statement is very important, when the cells are said to be, when cells are said to be connected in series. Positive terminal of one cell is connected to negative terminal of another cell, or the negative terminal of one cell is connected to positive terminal of another cell. Then cells are said to be connected in series. If the cells are connected in series, then the current drawn from each cell is same terminal potential difference. Terminal potential difference across each cell. Terminal potential difference across each cell that is different, and the net terminal potential difference. Net terminal potential difference across the series combination that is exactly equal to the sum of terminal potential differences, sum of terminal potential differences across the individual cells. Okay, and this is actually the equivalent circuit of this series combination. Okay, so this is the equivalent circuit of this series combination. So this one having the equivalent EMF is EQ and internal resistance is R AQ. So this is actually the point A. This one is the point C. So what is the statement? One, two cells are said to be in series. The positive terminal of one cell is connected to negative terminal of another cell. Then the cells are said to be connected in series. So if the cells are connected in series, then current drawn from each cell is same. Terminal potential difference across each cell is different. Net terminal potential difference across the series combination is equal to sum of terminal potential differences across the individual cells. Okay. First here, let us consider equation that is V A C that is equal to V A B plus V V A B plus V B C, right? The terminal potential difference across series combination that is equal to sum of terminal potential differences across the individual cells. So here first we have to calculate the terminal potential difference across cell 1. Terminal potential difference across cell 1, that is VAB. So this can be calculated by using the formula, that is VA VA V is equal to E minus IR. Okay, so here VAB, terminal potential difference in terms of EMF, current, and internal resistance. So here, what is the EMF? EMF is across the first cell, E1. Okay, minus current is I, right? So what is the internal resistance of the first cell? Is R1. Call this as equation number 2. Okay. So next step, the terminal potential difference across cell 2, second cell, that is VBC is equal to E2 minus, so here what is EMF? E2. Current is same, I, but internal resistance is R2. Call this as equation number 3. Okay, so now substitute equations 2 and 3 in equation number 1. Equations 2 and 3 in equation number 1. Then we get VAC, that is equal to VAC is equal to VAB is E1 minus I into R1, right? Plus VBC value is how much? That is E2. E2 minus I into R2. Okay. And then VAC, that is equal to E1 plus E2 minus I is take it as common. So minus I of how much? Minus I of R1 plus R2, right? Minus I of R1 plus R2. Now, if the two cells are replaced by a single cell having the equivalent EMF E, AQ, and internal resistance or EQ. Equivalent EMF means EMF of a single cell which produces the same effect as this combination. Equivalent EMF means EMF of a single cell which produces the same effect as this combination. So this is equivalent internal resistance. Okay. If two cells are replaced by a single cell having equivalent EMF EAQ, then what is the value of VAC? VAC is equal to EAQ minus I into RAQ. Okay, so call this as equation number. Actually call this as equation number 4, and call this as equation number 5. Okay, this is equation number 5. So now comparing the two equations 4 and 5. Now comparing the two equations from equations 4 and 5. So then we get, so what is the value of equivalent EMF? Equivalent EMF is E1 plus E2, right? E1 plus E2, and equivalent internal resistance or EQ value, comparing these two equations, or EQ is R1 plus R2. Okay, these two equations are very important. So this is the equivalent EMF of two cells connected in series. This is the equivalent internal resistance of two cells connected in series. Suppose if n number of cells, are connected in series, then what is the equivalent EMF? So that is also very important. Suppose if n cells are in series, then the equivalent EMF is E1 plus E2 plus E3 plus so on up to En, and equivalent internal resistance, that is R1 plus R2 plus R3 plus so on up to Rn. Okay, if n number of identical cells, if these points are very important, if n number of identical cells are connected in series, then what is the equivalent EMF? So in this case, the equivalent EMF is EMF is NE, right? If two cells are connected in series, each one having EMF E plus E, 2E. Three cells are connected in series, each one having EMF E, that is 3. N number of cells are connected in series, each one having EMF is E, then the equivalent EMF is NE. So then what is the equivalent internal resistance? That is NR, N into R. Okay. Suppose the positive terminal of one cell, this is very important for CET, the positive terminal of one cell that is connected to positive terminal of another cell. Okay, so this one having EMF is E, this one is also having EMF is E. Then what is the equivalent EMF in this case? Actually here the first cell, suppose E is positive, the second cell EMF is negative. This is the wrong connection. Okay, we should not connect the cells in this way. Okay, so positive terminal of one cell that should be connected to negative terminal of another cell. So this is wrong connection. Positive terminal of one cell is connected to positive terminal of another cell. Suppose this one having EMF 1.5 volt, this one having 1.5. The equivalent EMF is 1.5 minus 1.5. So here E minus E, E minus E get cancels. Actually, the net EMF in this case is 0. Okay, these points are very important. When the two cells are said to be connected in series, the positive terminal of one cell that is connected to negative terminal of another cell. If the cells are connected in series, current drawn from each cell is same, terminal potential difference across each cell is different, net terminal potential difference across the combination, series combination, that is equal to sum of terminal potential differences across individual cells. Okay, thank you.